Well, we've got John Carmack from Armadillo Aerospace here with us. You had a successful flight yesterday with your mod, and then today you had the quad, which is a fun naming convention, the 4 quad. It didn't go quite as planned. So what happened today?
Well, it was obviously a disappointment, but as I told everybody yesterday, and some people saw an earlier email assessment of it, we only got 10 days of testing before we were able to get here because of the whole issue with the FAA reclassifying our tethered tests as needing launch licenses. So we came here expecting to do 2 months of testing before this, and we wound up with about 10 days. So we foreshortened it, but we still felt pretty good. At the end, though, I had a list of about a half dozen things that I thought if we had more time, we would try to address. There were things like the red computer box gyros drifted a little more and their batteries were running a little bit low. We were worried about a few other things, but the big kind of unknown thing that we really hadn't seen at all before we started this test cycle was we had been running into these problems with some of the valves not moving when they were commanded to, or moving very slowly. And we found we actually had conclusive evidence of this early on, where we had first one start where the LOX valve didn't move and the fuel valve did, and then one where the fuel valve did or didn't and the LOX valve did. And we spent a lot of time looking at current traces and things here, and we couldn't find an absolute smoking gun on this. So we changed a few parameters about how, when we start doing, kicking around gimbal actuators and stuff like that, and we swapped actuators on one of the other vehicles, and in the end we had gone and done several successful tests. We did 3 successful tests with Pixel after that, and a couple on the mod, and we thought that everything was, at least we crossed our fingers and hoped it was fixed, but we really wanted to get something where we nailed down under bench test conditions exactly what was happening. But it was a frustrating thing to do, because it was the type of problem, if we just tried to test the engine, all the actuators on the vehicle there, it never happened. It only happened when we were trying to actually fly the vehicle. We finally found we could replicate it in one case at least by pressurizing the vehicle. We could have had water or something in there, but it only happened right up at that operating pressure. So it was something really marginal, where only when there was enough pressure on the valves that they took a little bit more force would this problem start to show up. But we thought it was fixed with the new valves on there, and we came out, and it almost bit us yesterday with the mod flights, because the last flight attempt, when we were going in, making the return leg flight there, we had an abort combustion at the start, where it had actually done the exact thing we had seen before. The LOX valve throttled up and the fuel valve was sluggish, and it didn't make enough combustion chamber, and that's all benign. We've got all these inner locks, so it just says, well, the engine didn't start, recycle. And we tried it again the second time. It did the same thing, but it just barely caught inside our window on that, and we made the successful return flight and won the level 1. We were very happy with that. But when we did the flight with Pixel today, it started up fine. So the way the vehicle works is when we command the engine start sequence, it fires the igniter, makes sure the pressure is good in that, then it starts throttling up first the LOX valve, then the fuel valve slightly lagged.
Apparently you're a little loud.
Okay.
Thank you.
And then it verifies chamber pressure to make sure everything's burning properly. So Pixel went through it, passed all of that, and then we give it the throttle up command to go ahead and lift off on the ground and start rising towards 50 meters. And actually, usually we first lift it up just 5 meters or so and check the trim and things like that. But this time we throttled up. It was sitting at 45%, and the LOX valve went all the way up to full throttle like it was supposed to, but the fuel valve moved at about half speed. So that meant we had 50% more LOX in there than we had fuel, and the engine is cooled by fuel on the outside, so it was both running very lean, which makes it hotter, and with less film cooling than it should have, which protects the engine less. So just as it was starting to lift off, it actually burned through the side of the engine, and that's one of those things that we've seen these things before. Whenever we wind up running lean, like we have on the rocket racers, we have fuel depletion sensors, because we did this test explicitly one time. What happens if your fuel starts glugging helium and it runs out, and it completely destroys the engine? We did that on purpose once just to kind of have a sense of how dangerous it was there. But we don't have fuel depletion sensors on this, because if it's in the air, we want it to die trying coming down. We don't want it to shut itself off and say, sorry, I'm about to burn through, when it crashes to the ground. But because of that, we did take the time to put some extra layers of insulation on the bottoms of the tanks, because we were a little concerned that if we had to burn through, it might make a jet of fire and burn through the tank, which would be a much worse thing. But that turned out to be exactly what happened. At 45% throttle, throttled up, went really lean, burned through that. It was still making a lot of thrust because it was good combustion, just very lean and very hot. So it was starting to lift off, but the jet of fire on the side pushes against the other gimbal actuators on there, and we can see the gimbal actuator fighting maximum force against that, but it's the engine makes more force than the gimbal actuators do, and it pushed it over the side, just kind of dumped it over on its head. It turned out that we kept telemetry through the whole thing. We didn't lose any pressure through it. As soon as it tipped to like 15 or 20 degrees, it started shutting everything down, and everything was shut by the time it hit the ground. It crunched the electronics box a little bit, but didn't disturb the computer. So we got it back over, detanked everything, and as I was looking at all the data traces, and we saw it was the same problem that we were worried about there. And it may have been caused more often because on this case where the gimbal actuator was working kind of hard as it was throttling up on there. We think there's something to do with that, but we've had the scope on this in like practically every place, and we haven't found a smoking gun yet for this. But so we made the decision there. The vehicle, we brought a spare engine. We brought a spare engine for each vehicle. We didn't have to use it for the mod. We have all the spare parts we would need to put everything back together. We crunched like one of the remote cameras, but we certainly could have had it back together ready to fly in the afternoon. So I proposed making a modification to the software to watch the valves and just basically never throttle the locks up if the fuel valve's not catching it, which would have saved us in this position where in that case the fuel valve was moving, the LOX valve would have just kept pace with it, and that would have eventually throttled up. But the case we were worried about then is, well, it's not just throttling up. What if when I'm going up to 50 meters and I'm saying, okay, now I want to stop on there, if the fuel valve is going really slow, then it might shoot up to 80 meters before it comes back down. And even that wouldn't be that bad. That would just be a little bit disconcerting, but the real problem would have been if we moved over to the other side and then we start our descent. It descends at about 5 meters per second, but then it has to throttle up to kill the velocity. So if we had a problem with the valves moving at half speed or something on there, then if it was going down there, it would try to throttle up and it wouldn't make enough thrust, and it would probably go ahead and go down and hit the ground. Now that should be a survivable rate. I mean, 5 meters per second, we could drop it like that. It probably wouldn't break anything, and it should be throttling up to some degree, so it probably wouldn't be the end of the world there. And an argument could be made that it would have been, all of our safety stuff still would have been in operation. It would have been safe, but there's more opportunity for us to damage the vehicle there, and it really is just a roll of the dice there. Since we know we've got a problem, we see it across multiple boxes on there, we can see it in our historic traces. It's something systemic and endemic to our systems. We believe it's in the electronics, although the fact that it happens mostly on the fuel valve is still sort of, well, we have several clues to get here, but by no means do we have the actual smoking gun where we can just point at it and say this part is driven at the wrong voltage or something. So at this point, all of our vehicles are grounded because the rocket racers use the same electronics drivers as this. We think it's a driver problem. The reason we believe we don't see this problem more on the rocket racers is we have the gimbal actuators and other things going on here. So there's a lot of other things that the driver board's doing, but this is not something that we want to be right at the margin on. We want to find out exactly what the problem is, and then we want to make sure that we have a 2x margin or more on any of this stuff so that we're not even close to having this issue in the future. And as long as we can reproduce it on the bench, and we believe that we can at a high pressure system. It's unfortunate that we can't just stick the valve down there and do that, right. But on the vehicle at least, fully pressurized, we've been able to catch the problem before. Although we replaced the valve and it didn't show up there, so it's something we have to statistically do at least, do it a bunch of times till we catch it. And we're going to try setting up better test harnesses, like we'll try setting a valve up with 800 PSI inlet and see if a valve by itself can cause the problem. But as soon as we can reproducibly perform the error on here, we'll just have a lot of scopes on it. We'll find out what the problem is, and Russ is a top-notch electrical engineer on there, and we'll make sure that we have overbuilt parts on this, and it will be a dead problem soon. Peter?
John,
yeah.
I'm out of here, buddy.
Hey.
Look forward to giving you another flight window for this competition as soon as possible. So the team is already talking about how soon can we open up the competition for the early part of 09. Realistically, I don't know how the window in 08, but as soon as we can in the first part of the year.
Okay, that'd be great because we go out here, we learn things, but it does kind of stink to wait a year to have the next attempt.
So the goal is to open it up for all the teams equally in the early part of 09 and figure out how we do that. But the quicker that, we can all celebrate your success. We can all and we all look forward to celebrating the next.
At the end of the day, we're all pretty happy.
Yeah.
I mean, we got the level 1 on there. We came out of this without a bunch of wreckage on the back of the truck, and the issue of top concern for us was exactly this. We had this mystery problem, and we've at least got a couple more data points that help point us towards it. So this would have been a debugging flight that would have been happening at our home base on here, just happened to be happening here, and that's really not the end of the world.
One of your great hallmarks, and I hope other teams see it as well, is doing everything in the open so the community can learn together. Anyway, thanks. I'm out of here. See you soon. Talk shortly.
Peter.
Bye.
Yeah.
Thank you guys for your webcast. Excellent work.
Thank you.
Much appreciated.
Thank you, Peter.
Thank you.
So it sounds like it's replicatable, which is good, because when you have a problem that you can't replicate, you don't even know where to look.
It's a little bit of a Heisenberg in that, it doesn't always happen, and sometimes when we're looking for it, it doesn't happen. But, in the fact that it happened in essentially half the tries that we had out here. The first two flights did not show any sign of it. The third one on the module did, and then the first one on Pixel did. So it's not the most fun type of bug to trace, and again, it only happens under pressure. It never happens just dry on there. So under pressure of multiple kinds, I suppose.
Well, one thing I think is fun, because you have a little background in gaming, just a small one. You use a joystick to control the vehicles. Is that
Actually,
correct?
we no longer do. Up through the last year, I used a Microsoft Sidewinder joystick, and it was kind of nice. It had all the buttons, and I could trigger all of the different actuator tests on there. But we were always kind of worried that that's one more thing that can go wrong. It's a little USB port, plugged into the side of the laptop. So this last year, I did switch over to all keyboard controls for things. And it's not like we were zooming it around like a fighter pilot on there. We were using the joystick more or less like a keyboard. We'd be looking at the downward-facing camera and be like a little to the left, bang the joystick over and let it come over, because it's not really responsive. It's intentionally tuned to be slow because we're always worried about tilting too fast. While we could command it to really drive around like the joystick and be zooming around, we have these fairly tight abort limits on our angles for all of our safety systems on there. So we've always been we want it to go slow and steady and not try to tip too far. But yeah, we were always worried that the joystick would break out the USB port or something, because we've got so much stuff sitting in the van as we're doing all of these operations, and it just made sense to cut that down to keyboard ops.
What's funny is most of my hardcore gamer friends prefer the keyboard anyhow. So
keyboard and mouse, the working in tandem is the way to go.
Yep,
there.
absolutely. So any other issues with the vehicle? Because I noticed that it was the mod was spinning a little bit, and maybe that was normal, but I usually attribute that to some sort of sloshing of fuel.
No, so we actually we have very loose control on the roll thrusters intentionally, where we can dial that number in and make it just sit perfect. But to conserve roll thruster ullage gas, we let it rotate. It can rotate 360 degrees, but we have very loose bounds. At about 45 degrees, it'll go ahead and kick it back a little bit, and that's just one of our decisions about. It's great. It barely touches the roll thrusters. It gets a little bit of a tilt there. It fires the roll thrusters only 2 or 3 times over 90 seconds. Now Pixel, because it's got the slosh issue, and that was something we only learned after building Pixel, that the multiple spherical tanks like that can really get the propellant sloshing around. And if we had gotten to see the flight here, it's kind of disconcerting where it starts off fine, but especially after it's gone and tipped over, or even after it's just sat there for a long time, it really starts doing a big slosh on there, and the gimbal's wildly moving around, and it's obviously something we're never going to design a vehicle like that again, and we found that out during Pixel's development. So the modules all have slosh baffles in them, so they don't suffer from that problem. But that's one of the other high concerns on Pixel, is that it's never caused an abort, but boy, it shakes around, and it does shake fast enough that the roll thrusters wind up kind of going out of phase to try and counteract that, and that saps our ullage pressure and gets us a little bit closer to our thrust margins at the end of it.
I'm continually amazed at, SpaceX had a very similar issue with sloshing.
The funny thing was, we saw that exact thing. It was a week or two before that SpaceX launch, where it was after X Prize Cup last year, I think. Or the year before, but the first time we did the year before. It was the first time we had done a ground liftoff touchdown with Pixel on there. We had set it up to go ahead, and we had transitioned over to a different type of feet that didn't break like the first one on there. So we brought it up, and we were doing a 180-second test there, and that was the first time we were really seeing it kind of shimmying around like that. Like, wow, that's a problem. And it was less of a problem with Pixel, at least because it had 4 tanks on there and they wouldn't go in sequence. But when we were watching the webcast of the SpaceX flight going up there, that looks just like our slosh problem. And in a single tank, it's worse because the entire mass is going around in sequence there. But that was one of those things where, and after the first SpaceX launch, we had our problems with cracked fuel fittings and fires and stuff like that. So we are getting to learn a lot of the same lessons, just on the cheap. Much cheaper and in similar time frames, more tests on our side, but of smaller scale. And we saw that a couple times.
Let me open this up to the webcast. Do they have questions for you?
Yeah, well, you addressed like most of them. So there was like, will you be augmenting the tanks to prevent the sloshing, or to at least help with it?
Okay, so a couple things on the slosh there. We cannot reasonably adjust pixel like that, but we found out also during the development of the rocket racer that originally we had set the rocket racer up with a big flexible flop tube so that you could pick up fuel if you're inverted or any kind of crazy aerobatic maneuvers, but it turns out slosh is a pretty significant problem for that too. Our future rocket racers will have slosh baffles and a fixed pickup with a kind of a sump arrangement, but we are considering some possibilities for for modifying the rocket racer with adding some things into the tank. We might stick in little things like rashid rings or burl saddles or something made out of Teflon, so we could stick them in to reduce the slosh. And we're doing a bunch of experiments right now. We've got a bunch of open hemispheres that we're just putting things in to check on that. But we couldn't do that for Pixel because we can't afford to add like 40 pounds of stuff in the tanks to reduce the slosh, because it is fairly close to the margins on what we can manage there. So Pixel, it still seems to manage it, but it's clearly a 3-year-old vehicle for us. There's a lot of things that we know now that we would do differently there. And there's even the temptation that the module flies so much better and is easier to work with and all of this stuff. We would at least consider, like certainly if we had damaged Pixel enough to not fly again, we would do level 2 by taking a module and adding a high pressure helium tank to it and just adjusting our dip tubes, because we have enough performance to make it on that also, and boy, it's an easier vehicle to deal with. Just there's things that you learn each generation there, and the modules, it's in Trooper now, it's still there, it's probably going to come back and fly again, but there's not much more we want to do after this. If we can take the level 2 with Pixel on there, it's probably just going to go to a museum and sit there.
Cool.
Somebody did suggest that, actually.
Yep, said earlier today.
If there's not too much damage, we can put
with all the dents, probably going to go to the New Mexico Museum of Space stuff.
Other questions from the webcast?
Okay. Again, you pretty much addressed most of it. Assuming that you do win level 2, which doesn't seem to be really all that far off, what's next?
Well, we've actually got a really full plate on our hands right now. We've got the rocket racers, where we're supposed to build 5 more of those in the next year, so they can start having big races of lots of them going on. There's a little bit of development going into. There's a handful of things we know we want to improve from our prototype on there. And then we just announced this larger deal with Rocket Racing Inc. and the state of New Mexico to develop suborbital passenger carrying vehicles based on these systems. So there's going to be a lot of commonality between that, and it's going to allow us to do things like start making batches of 20 of some of the parts that we make. And we've still got NASA work with the LOX methane, which is important for us in the long term, because we believe that once we get the reliable suborbital work, as we start heading for orbital work, it's probably going to be a self-pressurized LOX methane upper stage. And so we're working with NASA on some engine development, and that's actually not gone nearly as well as I would have liked. We were hoping that a lot of our alcohol experience would carry over there, but methane gave us a lot more trouble. There was things that we expected. The second cryogen, more probability of leaks. You can get little fires when you've got methane leaks that you don't get with LOX leaks, and it turns out to actually be a little harder to ignite. You wouldn't think 2 gases, LOX and methane, would be harder, but they're very, very cold gases in there in the chamber, and we actually had to upsize our igniter a little bit. And those were the types of things that we expected. But what was unexpected is we have some serious combustion stability problems with methane, where we finally got an engine that would run fine full throttle on the test sled. So we put it on one of the modules, and we were starting to do hold down tests on it, because the goal is to actually fly a vehicle around controlled like this on a LOX methane engine. But what we found is, okay, it's fine at full throttle, but then when it goes to a part throttle on there, it gets an instability, a screech there, which is very high frequency, because all my transducers say it's perfectly smooth on here. But we come over there and it's vibrated out the spark plug and the gimbal actuators and a couple of the swage locks on the pressure transducers. So we're making a change to that. That's when we get back, our top priority is figure out this voltage, this driver problem on there, because that affects everything. Everything uses these things, and we're not going to fly anything, not a NASA project or a rocket racer or one of these, until we really have that absolutely nailed down. But the next priority probably is getting the methane work finished up so that we can go ahead and take it to the point where there's many stages that we want to try there. We want to fly a vehicle on it for NASA to kind of have done that. But the things that we're looking at into the future with methane is the possibility of, instead of using helium overpressure, using the LOX in the methane, allowing them to self-pressurize up to 200 or 300 psi. That turns out to be about a wash for a ground liftoff in terms of performance. But if we do that, it lets us get rid of methane, or get rid of helium in our supply chain. And helium is the most expensive single thing that we wind up using. It's probably nearly half of our operating costs on there.
Oh, wow.
So the methane, that could be a significant savings there. And there are future possibilities of things that we can do with LOX methane like that to simplify our ignition systems and to to simplify removing purge systems and other stuff there. And again, the long down the path stuff, we want to be doing these really lightweight, very thin, low pressure LOX methane engines for upper stage work. But after we get done with that, then it's probably back on the rocket racers, finishing the development of the engines. We're making only very slight changes to these engines for the suborbital work. They're getting a couple more elements in them, and that is the comfortable place, right around 3,000 something pounds of thrust, and we expect to stay there really for the foreseeable future. We're looking at a cluster of 8 engines for the suborbital vehicle, arranged as 2 sets of 4 engines, so we don't need roll thrusters because the engines are canted slightly, so you can balance between it to get roll thrust from your main engines. Because I've always been worried for the high altitude flights as we go fast that we have cold gas roll thrusters now, and aerodynamic asymmetries could start just make one stay on the whole time and deplete the ullage pressure. So we really want to get back to using engine thrust for roll control as well. But the next flying vehicle project, after we get done figuring all of this stuff out, is taking 4 modules. We've got all 4 tank sets, putting an engine on each one, taking the gimbals off and replacing them with fixed tie rods at these thick cant angles, bolt all 4 of them together, and do testing with just differential throttling the engines, throttling them up and down to do that. Now, we did that years ago on our peroxide-based vehicles, but we haven't done that on any of the liquid oxygen vehicles. We have every reason to believe it's going to work well. The response rates are very good on this, but we need to prove that out because that is our baseline right now for the suborbital vehicle. It's multiple differentially throttled engines. So that'll just be a hover test under tether, make sure we've got everything worked out there. Then we'll break the modules back apart and start going up to the Oklahoma spaceport first to fly the modules fast. Start off on there, but instead of going for 5 meter per second ascent, it's going to be start out 5 seconds full throttle, see how high it goes, then it throttles down. It'll be engine on the whole way initially, and we will bump up that thrust period until we get to, we're cleared for about 5,000 some odd feet there, which isn't real high, but we can still, with light propellant loads, we can punch that up to 200 plus miles per hour, which is about the effective airspeed we expect to fly, 200 to 300 knots effective airspeed for the suborbital vehicle. It's going to be a low and slow vehicle because it's big and draggy on there, because we want something that's not going to tip over real easy on landing. But so we'll initially go through boosting that up till we find out what our upper limits are in that environment. Then we will probably try a shutdown and engine relight in Oklahoma. That's going to be a nail biter. Go up there, Apogee, shut the engine off, let it come back down and restart before it crashes into the ground.
I want to watch that. That's going to be awesome.
Yeah. But then it's going to be heading back out here to New Mexico. Hopefully Spaceport America will have all of their final spaceport permit environmental assessment work done, and then we'll be taking the modules out here and loading them all up and flying them as high as we can go initially in the base configuration, going for reusability. And we've got 4 of these. We expect, I would be stunned if we don't make some smoldering piles of wreckage in the way here, because there's just things we need to learn. But we've got 4 sets of these, and I really do think we're going to work out all of those by the time we get to the end of that. And once we've gone through and kind of got them reusably flying to whatever altitude they'll go, and with the big legs and in their base configuration, it's not going to be super high, but it'll be going many tens of thousands of feet high. We will then probably take the legs off of a module, start it on a stand. We've got a nose cone for it, and if we put a pressure tank in the nose up there, and fill the tanks all the way full. That should be a 100-kilometer capable vehicle there. That would probably be recovered with a parachute because it won't have legs to land on. Because we want to go and hit the bogey. You know, we've been to 100 kilometers with a vehicle that we can derive the kind of heritage of technologies going from that to the suborbital vehicle. And we expect kind of simultaneously with that, once we've done the 4-module differential throttle system, then we know that the core direction that we're going for the suborbital vehicle is okay. If we can't make that work, then we have to do something with gimbals, and the vehicle design will change. But as soon as we've proven out the differential throttling, we will be starting fabrication on a full-scale suborbital vehicle capable of carrying 2 people to space. And I would expect that simultaneous with all of these module flights going on, that will bring up into hover test, hopefully towards the end of next year. And then once all the testing's done with the modules and they're put away, we'll be taking that full-scale vehicle through the same paces, go up to Oklahoma, fly through 5,000 feet, and that's just because Oklahoma is less than half the travel distance for us. It's a long haul out here to New Mexico, but when we're aiming for space, it's going to be out here. And they're not going to be that expensive to operate. We believe in, instead of mounds of analysis, mounds of data, and we want to have lots and lots of flights. Now there's going to be a lot of flights before we start fulfilling just random ticket buyers. I want to get on this and go. But there's a lot of opportunities for things earlier. We're still psyched about like the space diving stuff, taking crazy skydiver daredevils up and breaking Kittinger's record that stood for 40 years.
Cool.
And there's things like that. There are cargo options of other things that we can do during the development on here, but the real push is for the manned suborbital stuff. That's what we've been pushing for since the very beginning. And it's been nice that we have turned the corner here. Armadillo's been operating in the black this year without any additional money from me, even before we won the prize. I mean, the prize is gravy right now. It gives us a lot of margin for things. The new deal that we announced with Rocket Racing in New Mexico is going to be a robust funding for the suborbital development. Without that deal, we carry on at our own pace. We've got our set of things that we do. We've got the half-dozen things we're juggling with business development on here. But basically, this deal allows us to say we're not looking for any other work. We've got the funding necessary to go forward, and we can devote all of our efforts there. About half the team is working full-time right now on there. We've moved to a large facility. I mean, the facility's big enough we could put a Falcon 9 in it. We've got a huge hangar outside Dallas now. It's going to be filled with rocket racers as we start going through all of this, but we've got a lot of space there. And we're bringing the crew on. Almost certainly there's going to be some more people going full-time almost immediately when we get back. We've got the extra cushion now to not worry so much about making payroll on there. So things are going well. It would have been great if we took the level 2 here. Yep. But it's
a little bit of a bigger purse.
Yeah. I mean, it's okay. We're happy that we got through. We would have been pretty bummed if I have a lot of empathy for Elon. Every year I'd be having the email back and forth with him. It's like, okay, second time for sure, third time's a charm, and God, I hope it works now.
So, your suborbital stuff that you announced yesterday, at least we saw yesterday, was really exciting to me, at least, because you talk about all the getting up there, but you didn't mention it's a giant dome. I mean, you could put 2 people in this thing, and it's just almost a 360
yes,
degree
well,
view.
The caveats that I've been trying to say is that when this all got put together, they wanted something really fast, and we kind of fudged up the one of the earlier concepts on there. That's likely not the exact view that this vehicle is going to be. We have to make the decision on fixed versus gimbaled engines on there, and that one was originally for a 1-person vehicle. We had 6 engines, 6 modules on there. The 2-person vehicle is almost certainly going to have 8 engines in there, and that also allows us to go to getting the roll control from the engines. With 6 engines, we would have had to have roll thrusters, because you can differentially throttle for attitude on 3 engines and have redundancy there, but you can't get roll with it as well. So it's definitely not going to be exactly that picture. So it's probably going to be 8 engines, and we're still debating whether it's going to be 2 tanks, 4 tanks, 6 tanks. There's all these options, where the thing that we're fighting is the narrower you make it, the more efficient you are drag-wise. So if we have 2 tanks stacked on top of each other with a ring of engines, that'll have low drag and have very little problems getting up there. But then you worry about falling over on landing, and you don't want to have somebody take a 10-foot fall over on there if something doesn't work right. So we're pushing towards trying to be lower and slower. We'll learn a lot from these high-altitude flights of the existing systems, but I'm hoping that we wind up with something that that will be lower. It might almost look like a megapixel with 4 tanks, but the key difference is,
Yeah, I like that.
yeah, I know. The key, they'd be bigger, larger tanks on there with like 4 times the propellant capacity on there with 8 engines still around it. But that would keep that really low. And then what we do is we start with a minimalist cabin on there that at the start, it would probably be a fiberglass cabin that goes into a nose cone to give us some streamlining on there that goes out to cover everything with like a 360-degree band of Lexan windows on there.
That's
but
awesome.
if it turns out that we've got performance margin, so we go and do that if, say, hey, we're coming back with 300 pounds of propellant on there, then we start stretching it out. And just until we balance out how much propellant you want to land with, we can keep making the cabin bigger, more volume, more space to play around in on there. And that's going to be one of those things that we can kind of interchangeably do with this, where we'll have all the propulsion stuff on the base and the cabin is going to sit down and be kind of pulled down on top of it. And there's still a lot of things to be determined with. Certainly there's going to be a ballistic emergency parachute on there. So the idea is you're coming down and you try to light all the engines at 1,000 feet or whatever. If one of the engines doesn't light, you just work on one quad. If 2 engines don't light on opposite quads, then you fire the rocket-drawn parachute and you come down swinging wherever you land on there. That's not intended to be the operational behavior of it, but all those things have to be worked out. But we have quite a line of people ready to get on these rockets and go. People that watch them right now.
Podcast from there.
Yeah. I mean, like at our Caddo Mills facility in Texas, we've got across the airport. There's a bunch of skydivers over there. They're all like, "When can we get on?" And, yeah, and one of our rocket racing liaisons has an incredible number of high altitude jumps and all this stuff, and he wants to be the first space diver. So it's not safe yet. There's no question about this. But
well, I don't think there's any doubt in anyone's mind that's not safe.
No.
Yeah, and one important thing that needs to be shown is that even if we demonstrate 100 perfect flights in a row there, if somebody's getting on there, the kind of rule of thumb for estimating reliability on there based just on data is assume the next one fails. So if you've done 99 successful flights in a row and you want to get on there, you have a 1 in 100 chance at least, at a high confidence level, of the vehicle having a failure that has not shown up in the previous ones. So this is orders of magnitude different from from any kind of traditional aviation or even from skydiving or hang gliding. Skydiving and hang gliding are much more dangerous, obviously, than flying on an airplane, but they still have tens of thousands of data points, and they come out and say, well, maybe 1 person in 30,000 dies doing this. And you can look at that and say, okay, those are numbers I can live with. But the early set of people that are getting on the suborbital rockets, they are going to be pioneers. They are going to be taking risks. It's not like tying up and going bungee jumping there. These are new vehicles, but it's economically impossible for us to develop a vehicle that could demonstrate the level of confidence comparable to aviation. We can't do 100,000 flights before somebody gets on. The business case doesn't close on there. But there are people that are willing to take that risk because it's going to be exciting as hell. It's going to be an experience. 500 and some odd people have been to space. So the first 500 people that are getting on these things, they're going to be able to say, I was one of the first 1,000 human beings to reach space. And that's worth a risk for a lot of people. The people that are going up to the space station on there, Richard Garriott just got back, and his risk was probably 1 in 100 or 1 in 200. That's astronauts flying into space. Those are the risks they take.
Space shuttle's 1 in 80.
Yeah, and it's worth noting that NASA never estimated it was 1 in 80 on there, so nobody should trust somebody going down, doing the numbers on the paper and saying, the mean time between failure of this is this and this is this, and running all the numbers together and saying Ares 1 has a 1 in 2,000 chance of having an astronaut fatality. It's bullshit, and that's, that things have to be grounded in reality. That is one of the kind of sicknesses in the aerospace industry is people, and I used to get this comment all the time, can't you do this on computer? Can't you just simulate this? Why did you have to find this problem out in test? And this mostly comes from people that don't work with physical things. You would never find an IndyCar mechanic saying, couldn't we have just simulated all of this and found out all of these failures here? But so many people, including the bulk of the aerospace graduates today, they don't work on physical things. They work on CFD and FEA, and they work on their computers and simulations. And there's a big gap between that and reality. But that happens because usually you can go your entire career in aerospace nowadays and never see something through that actually builds up and gets flying on there. And that was the real cornerstone decision for Armadillo Aerospace at the beginning. Whatever we had to do, it had to be closer to software. If I had to write software in a way that I only got to build something and test it 5 years when the program was done, or do incremental unit testing, or check it once a year, you'd never get anything done. We wouldn't have the internet, we wouldn't have PDAs and all the magical things that we've got now, because you just couldn't get it done. So while it's true that you don't have the fungible magic of software when you're putting things together, you can make decisions at the high strategic level that allow you to approach that, where we have built consistently 2 completely new vehicles every year for the last 8 years, more in some cases. So we can go through complete design cycles in 6 months. And and the fact that we can go through and test, every day sometimes on there, multiple times in a day, that allows us to go through and learn some of these lessons. And yeah, there are some lessons that we could have learned by simulating on that, but in many cases, it's actually cheaper and faster to learn it in real life, and you have ground truth to work with there. It's not a matter of looking at something that maybe it's like this, trying to guide your simulation into reality, and that there are some things that work great for simulation. If you're doing finite element analysis on a milled part that came out of a block of metal, that's pretty damn good. If you're doing liquid flow through, a set of milled channels or something, CFD's pretty damn good on there. CFD simulating an engine is crap. Trying to simulate a welded structure out of all these different things where you've got heat affected zones and pieces out of multiple fabrications, that's not very good either. And in many cases, it's easier to just say, well, some people would say it takes an engineer to build a bridge that just barely doesn't fall down. And there's some truth to that. If you want to optimize all of your materials and you want to get 99-point-something% on there, that's when you go in, you try and analyze it all as much as you can, figure out, well, we only need cables this thick, we can get by with this. And in some cases, when you're talking millions or billions of dollars, that is absolutely the right thing to do, or when you have an incredible database to work with. But when you're doing something new, it's so much easier to say, well, this is probably about right. We're going to proof test it 50% over what we think it's going to encounter on there, and we will accept this being 20% off optimal. And that's just the ground rules, and say, well, everything else just has to live with that. We're not going to fall into this trap of saying, well, we need, we do wind up like the last week before we got here, when we were sitting around not having our permission to test on all this stuff, James did go around with a saw and carve 10 pounds of nickel and dime stuff off Pixel. Turns out we didn't need it at all. We landed with 100 and something pounds of propellant on there. But you can wind up doing that later. It is so much easier to build something and make it work and go from there, rather than to do what happens all the time, is try and design the perfect vehicle and it never happens. Looking at the government programs as you go through, National Launch System, Advanced Launch System, the Air Force programs of, Ares, Falcon, Rascal, FAST, all of these, hundreds of millions of dollars get spent. Hundreds of millions. Nothing leaves the ground. It generates mounds of paper, some test data, materials research and all this. No product, nothing that generates any value for anyone. And it takes so much less than that, but the total input for Armadillo now is, it's close to $4 million. But again, I haven't had to put any money in this year. It's actually been operating on its own here. And I look at it, what we're doing with how many people. We might staff up another 1 or 2 as we go through suborbital. We have all the skill sets we need. We might want more hands, actually working on things, building it as we're putting together sets of 8 engines, and we'll be building backup vehicles as we always do on there. It's not going to be the vehicle, and that's the problem with so many of the space tourism companies that you see. We need to raise 20 or 50 or $100 million, and we will build the vehicle, and it's a Hail Mary. They've got the vehicle. As soon as something breaks on there, they're screwed if they don't demonstrate everything they need to with that, and they aren't rolling in the money by that point, let alone paying back their investors and everything. So I really believe in that. Small team, building lots of things, testing it all the time, running with lots of backups, learning from reality.
I think, are we running out of time, or what's the...
That's my understanding.
Okay.
Yep. So really quick, in closing, you're talking about some really exciting things. This might be too early, but time when someone like me will be able to go up into space in one of your vehicles, and how much would that cost me?
the consortium going together here, the ticket price is established as $100,000 or less.
Oh,
so it's
you're
half of Virgin
yep.
Galactic's on there. Now, there's going to be plenty of people that will just never ride on a vertical takeoff vehicle. They want to land on wings. There may be a lot of people like that, but we feel the market is large, that we've got a line of people already that want to get on the vehicle, even in its current unsafe condition. After we've got 100 test flights on and redundant engines, that line gets a lot bigger. So we're not too worried about cutting the people out, but there is going to be a big price cut there relative to all of this. Time-wise, anybody that's heard me make estimates, I'm always wrong. So it's, but we make, as long as we're making progress on there. But the way I see it, next year we do a space shot with existing stuff on there while we're building up the crew vehicle on there, and then 2010 we have test pilots, obviously unmanned flights going in there, but probably some kind of a test pilot on the real vehicle. I don't know if that'll be worked all the way up to 100-kilometer manned shots there. I hope we actually do the space diving this coming year, because we can do that with our current stuff. If we bolt together the four modules,
cool.
If we haven't wrecked any of the modules in our testing there, we can still put 4 together, then we can probably take the guy to 120,000 feet on existing hardware.
Cool.
And again, we've got, there are people raring to go. And I won't feel too bad about putting a skydiver on there, somebody that has the right stuff, so that like, even if you look at the stuff here, if it bailed like Pixel bailed today, they do a little dirt dive out there, and that's, that's okay. And as long as they've gotten up to at least several hundred feet on there, which, we haven't had a problem in that vicinity there, that they should be able to go out, and we could probably even arrange to have abort options at earlier things. Maybe we can do it taking off from a barge, so they can be cliff diving if it fails earlier. But I think we can work some things out that we have gung-ho people that are interested in doing that. But I would hope that we're doing it at passenger flights in 2011. But we'll see how it goes. And we've got milestones that we're aiming for in here, and I'm trying to turn over a leap and be pessimistic. My wife gives me crap about this all the time, where whenever you hear a programmer estimate something, double it.
Oh yeah, and, absolutely, yep.
And she has the programmers working at her company, and that's kind of what she does in her head there. And for a long time, I was proud when I just missed by 50%. Hey, I'm doing great here. But
we're still talking before 2020. We're not talking 2030, 2040, 2050.
It's early soon, and exciting things are going to be happening all along the way. We should be having all this stuff, like first space shot, first space diving, first flights of all of this. So there's going to be fun milestones to be following along with all of this. And then as we look long term, there's a long term plan. As we get through this with the vertical takeoff vehicles, where we've got more performance margin, we're going to see what it takes in terms of performance, what we've got in terms of additions that we can make and improvements and mass ratios. Obviously, Rocket Racing Inc. is interested in eventually having a horizontal takeoff and landing vehicle. And the bottom line is that's harder. There's just no two ways you can slice it where it's not a harder problem to do that from a propulsion standpoint. The wings weigh a lot. You're not the best shape. If a rocket doesn't look like a bunch of flying fuel tanks, it's not a very good rocket. It might be a better airplane and a not so good rocket. But we'll see how we are, and maybe the second generation vehicle goes like that. But we're not qualified. We've learned a lot about airplanes just working in this last time, but we're still not airplane guys. We would have to work with another major partner to do something like that. But then the direction that we want to go, left to our own, there is we've got a 100-kilometer elevator, goes up and down, take 500 pounds of passengers and stuff out of there, and put in a 500-pound upper stage. And we know we're looking LOX methane, thin tanks. We know how cheap we can build these. We don't care if we fail 10 times. We can afford that going through on this type of thing. But eventually we get our little Sputnik in orbit there. That's just the flight computer beeping, I am here, on a satellite, cell phone on there. But then, once we've proven that out, then we can start scaling things. We can modularly build the bigger suborbital vehicle, build bigger upper stages, until we can get to doing something useful in orbit. And again, prove out all the technologies. And even if that's not soon, that's a ways down the road. And I don't spend too much time talking about all the great stuff we're going to do in orbit, because there's a lot of steps between here and there. But we know how much we're spending. We know how much it takes to build these vehicles and build vehicles that are multiples of this size. It's not going to be that much money out of my pocket. And again, hopefully no more money out of my pocket. Hopefully, Armadillo is carrying its weight now, and we have every reason to believe that that's going to be the case going forward, that we make enough profit on here to fund all of these things. But even then, the total amount going into it, it's going to be I think we're going to put something in orbit for $10 or $20 million of money put in there. It's not going to be something useful. It's a Sputnik. It's to show that we've done it on there. But learning the lessons like that for this tiny amount of money, I'm still young. I'm 38. We got a lot of time before a moonshot on there.
Well, it's you're a fascinating company to watch. It's one of those world-changing type things. Everything in space travel is going to change based on what you're working on right here today and now, and it's fun to see. You're clearly passionate about it. It's fun to watch, and it's been a pleasure sitting down and talking with you today. So I hopefully sometime in the future we'll be able to bring you on the show once again. So.
Well, I hope we get to do the LLC Level 2 again fairly soon. Get you out here.
That'd be great. Yeah, absolutely. So thank you so much for your time with us. Have a great one.
Yeah,
Thank you so much.
All right.